Okay, looking here at the solutions of that fiendish looking equation where the gravity wave speed is square root GHN. That's all you have to remember, that they look very similar, but now you have stratified vertical column and has layers with depth Hn, and that couples the horizontal and vertical structure functions. So the equation has solutions of the form psi n equals an exponential minus 1 over psi squared hn psi, where psi whatever equals beta squared or GHN to the 1/4 of y. So this is the meridional structure we are talking about. So this is the Hermite polynomial. If you don't know what that is, you can look it up. But this is a series of solutions that add up to the structure function we are seeking. So we note here that determination of the latitudinal structure by Hn emerging from the vertical structure. So you have now the vertical and the horizontal coupling happening here. So the latitudinal structure emerges with Hn of the layer thickness and is a true solution of 539 when these conditions are met. So this is why this is a polynomial. Okay, so that's the Hermite polynomial. Okay, so that is minus beta k or omega minus k squared plus omega squared over GHN times square root GHN. So that is c divided by beta equal to n plus 1, where n goes from 0, 1, 2, and so on. So now you are basically defining modes of waves. Okay, it's a superposition of waves, as we will see later on. Okay, in this case now then v hat yz, the meridional perturbation velocity, is given as the sum over n of an zn as a function of z. So you still need to be consistent with the background state. That's the main thing to remember there. Exponential minus 1 over psi squared times the Hermite polynomial. Okay, out of that we can get forced and free solutions, but this depends critically on how the h bar is chosen. Okay, people have chosen all kinds of values, but it does have a significance in terms of the choice. For shallow barotropic fluid of depth h, we can write the Rossby radius of deformation as c or f. No vertical structure, it's barotropic, so c in this case is simply square root gh, the equivalent depth, divided by f, the Coriolis parameter. In a baroclinic fluid, we wrote that in terms of the Brunt-Vesala frequency, which is related to the vertical structure, and the scale height divided by f, right? So there is the difference that we have already seen, that we have g in our set of equations. So just as example, if the basic state is quiescent, then if you have equivalent depth of 300 meters and beta is 2.3 times 10 to the minus 11 per second per meter. Remember, this is df dy. F is 1 over second and df dy is 1 over second meter. Then you get Rossby radius of 1500 kilometers. But when you choose different depths, 25, 50 and so on, you end up with Rossby radius having values of 650, 1000, 1157 and so on, right? Remembering that Rossby radius is the scale of the rotational forces becoming comparable to the stratification forces, then these are important. So the stratification and how it's balanced in a rotating framework very much depends on the Rossby radius of deformation, which itself depends on the equivalent depth h. That's the main point. Okay, so for an isothermal atmosphere with temperature T bar, vertical scale Lz and h bar, they two are related through Lz equals 2 pi over k kappa, sorry, h is h bar minus 1 over 4 g bar. So you have the vertical scale height being related and the equivalent depth being related to the horizontal scale. Okay, so they are not, you cannot separate them. They are closely related to each other. That's the main point we should remember. Maybe I'll add a little bit more. That shows us the coupling. So if you look at the vertical wavelength LZ and the equivalent depth h bar, then you can see that as the equivalent depth increases, the vertical wavelength increases as well. Okay, that's the coupling we are talking about here. Did I say horizontal? I should be careful. Okay, so there are waves that are propagating horizontally, and then there are waves that are also propagating vertically. How is then h bar chosen? So looking at our equations from before, where we had just the horizontal motion, and we derived the equations, linearized them, and derived the harmonic oscillator equations, the equivalent version in this case emerges this way. Minus I omega u minus beta yv plus I k g h in the zonal direction. For the meridional direction, you have the slope of the layers, and in the forcing function energy equation, you have mu y, which is the coefficients of Fourier expansion mxyt, which is the real part of mu y times exponential ikx minus omega t. So in this case, the source and sink function is just the heating and cooling, right? That's all this is saying. So writing the perturbations again in terms of uv h y, that's what we did in 5.9 when we didn't have vertical structure, and we had a similar equation as this one. So you can see now d squared v dy squared plus this complicated function of Coriolis and wave number and frequency. You have the relation between stratification and meridional balance. Okay, so making the transformation psi equal to square root beta over c times y. So gravity wave speed and the Coriolis beta effect, they are related. We'll see when we see the waves, we will see that beta effect is very critical. Rossby wave is essentially because of the beta effect. If you replace air parcel, its vorticity changes, and the planetary vorticity or the beta effect is a restoring force, and then it can overshoot and then oscillate. So it's the relation between those sorts of things that is being implied here, but we are not doing physics, we are just running through the equations. So then we can write d dy and d squared dy squared in terms of this transformation, and we get this nice looking equation if you can make sense out of it. So d squared d psi squared equals this complicated function with c over beta minus psi squared times v. So again we have a wave equation with this function, forcing function on the other side. Okay, this equation now represents those modes forced by the distribution of mu y. How is the heating distributed in the meridional direction? I'm saying heating, but it's some forcing in the meridional direction. It could be the Hadley cell with subsiding, which is adiabatic compression, radiative loss, and so on. So we will not get there till we get into those details. So if the forcing is 0, then we obtain solutions that represent all possible oscillations within the system relative to the boundary conditions v equal to 0 at very large y. Okay, so we are still talking about the turning latitudes up to which you have waveforms, and then you have exponential solutions, and then v has to go to 0. That's the boundary condition. You cannot let finite flow at very large y, right? This is free or unforced equation then written in this form. Okay, as I said, the idea here is just to look at these equations and then try to come back to them in the context of the physics. Right now we are not talking much physics, we're just running through the derivation of the equations and looking at their forms when we have just horizontal background flow, and we have horizontal background flow as well as vertical structure. Of course, we are now linearizing about a stationary state, but perturbation flow is there, of course.